This module, Module 4, is the first of several modules covering topics in Chapter 2. So Chapter 2 in general covers Boolean algebra and Boolean equations. So these equations, Boolean equations, are the way that we specify the function of a digital circuit. And we'll also talk about logic gates, including multi-level, combinational logic, and other topics for minimizing equations such as Carnot maps and Klein-McCluskey methods. At the end, we'll talk about timing as well. So again, in terms of our abstraction levels, we are here talking about logic and digital circuits. So this module in particular is going to introduce Boolean equations. We'll also talk about circuits, basically functions and interface. We've talked about that before in terms of modules that have defined functions and interfaces. So we'll talk about that specifically in this specific type of module, which is a digital circuit. And there are two types of digital circuits, combinational circuits and sequential circuits. This chapter, Chapter 2, discusses combinational circuits, and then we'll come back to sequential circuits in Chapter 3 and talk about those types of circuits as well. So the main topics of this module are discussing Boolean equations, and there are two specific types of forms of these equations that we'll talk about: sum of products, SOP, and product of sums, or POS form. So the first topic is logic circuits. A logic circuit is composed of inputs and outputs. We've referred to this before as the interface of the circuit or the module. And it has a functional specification. So what does this thing do? And the final specification is a timing specification. How long does it take to do this thing? So we'll talk about that at the end of this chapter. So circuits are composed of nodes, which are signals. So for example, A, B, and C are all nodes. They're input nodes, to be specific. And the circuit also has output nodes, Y and Z. There are also some internal nodes, in this case 1, and 1 is an internal node. It's not an output or an input, but it is a specific signal or node. Each circuit can also be composed of additional circuit elements. So in this case, this circuit, this higher level circuit, is composed of submodules or subcircuits, element 1, element 2, and element 3. Each of those is in itself, those are circuits as well. So for example, E1 has interfaces, A and B are its inputs, and N1 is its output. So this is another example of the design principle hierarchy as well, where we have some system, in this case a circuit, composed of sub-modules or sub-circuits in this case. So there are two types of logic circuits. The combinational logic circuit that we'll talk about in this chapter, Chapter 2, like I mentioned before. And combinational logic circuits don't have memory, so they're memoryless. In other words, the output is completely determined by the current input values. So an example of a combinational circuit is an AND gate. If I know the inputs of the AND gate, so for example, there's a 0 on one input and a 1 on the other input, I can completely know without knowing anything else but the input values what the output is. In this case, if an AND gate has a 0 and a 1 on it, the output will be 0, independent of any prior input values. The output is completely determined by the current values of the input. So another example, if instead the input values are 1, 1, well, now I can know just by knowing the current values of the input, 1, 1, my output will then be 1. So I can completely determine the output values depending on just the current input values. Sequential logic, on the other hand, has memory. So a good example of a sequential circuit is your cell phone. So once you turn that on, it remembers some of your prior inputs. So it remembers, hey, when you press the contacts button, it remembers that in some prior time, at some prior time, you entered contact info for, some person, and you can click on that and get their phone number. And so in a sequential logic circuit, this circuit's outputs are determined not only by the current values of the inputs, but also by previous input values. And again, we'll talk about sequential circuits in Chapter 3. Okay, so let's talk about combinational logic circuits for this chapter in this module. There are certain rules of combinational composition. Every element is combinational. So here in the example below, we have 2 AND gates. Those are each combinational, and an OR gate, also a combinational circuit. So every element of the combinational circuit is itself combinational. A node is either an input, in this case, or connects to exactly one output. So it cannot connect to more than one output. So this node, for example, is an input and connects to exactly one output, but not more than one. So I can't do this, where it connects to 2 outputs. That would be an invalid circuit. So not a good circuit. It has to connect to exactly one output. The third rule is that the circuit does not contain cyclic paths. So the example below does not contain cyclic paths. Here's an example where a cyclic path from the output back to the input occurs. So that connection is not allowed in combinational circuit design. So that is also not allowed. So we can specify the function of these combinational circuits by writing the function in the form of an equation, and specifically in the form of a Boolean equation. So this circuit, this CL in the middle, means it's a combinational logic circuit. And this circuit happens to have inputs A, B, and C in, and 2 outputs, sum, or S and C out. I slipped and said sum because this circuit, given the equations below, actually specifies a 1-bit full adder. But at the high level, we can just think of it as having 3 inputs, 2 outputs, and our outputs, for example, the S output, is some function of the inputs A, B, and C in. The second output, C out, is also some function of the inputs A, B, and C in. And now that we know that these outputs are some function of the inputs, we can now specifically write what that function is. And here is a Boolean equation saying what the relationship between the S output is as determined by the inputs A, B, and C in. So in this case, S is the 3 input XOR of A, B, and C in. So it's A, XOR B, XOR C in. The second output, C out, is also some function of A, B, and C in, and specifically it's A and B, or A and C in, or B and C in. So we can specify the function of our circuit in terms of these Boolean equations. So let's talk about some definitions here before we dive into what the methodology is for specifying these equations. So first of all, we're going to talk about variables or signals. So the example we had before with A, B, and C in, we can have some signals, A, B, and C, as written here, and the value of those signals, well, it's a binary system, so the value is either 1 or 0. So A can have the value 1 or 0. And that way, these systems are actually kind of simpler than many systems we have to deal with, specifically analog systems. And that value is determined by the voltage on a wire. So for example, 5 volts for R1 indicates that there's a 1 on that signal, or that the signal value is 1, or 0 volts, which would specify a 0 value of that signal. So another word for these signals is also variables. So these variables, well, they can't vary much. They can either be 1 or 0. But they're variables. We don't know necessarily what they are all the time, determined by switch values, or if it's an output by the actual values of the inputs. But those signals are also, we can also call them variables. So we'll also talk about different forms of these variables, as well as different groupings of these variables. So let's define some of these terms that we're going to use the rest of this chapter and the rest of this course. So the complement is a variable with a bar over it. So for example, A bar, B bar, C bar. That can be said either A bar, so that variable with a bar over it is A bar, or you can also call it not A. So the complement is a variable with a bar over it. A literal is a variable or its complement. So A is a literal, A bar is also a literal. So the true A or complement form of a variable is called a literal. Now an implicant is a product of literals. Remember that word product, we've taken over that multiplication sign for the AND operation. So it's a product or AND of literals. So A, B, C bar, or I could also say that A and B and C bar is an implicant or a product of literals. A bar C is also an implicant or a product of literals. Now a minterm is a product that includes all input variables. So if our circuit has inputs A, B, and C, the minterm has to include some form of A and B and C in its product. So A and B and C bar is a minterm because it includes all of these terms. A and B and C is also a minterm. So remember, product means an AND term that includes all input variables. Max terms are sums. Remember, sum, we've taken over that OR operation, that OR symbol for, or the plus symbol for the OR operation. So max terms are a sum or an OR term that includes all input variables. So again, consider our circuit here that has inputs A, B, and C only. Then A or B bar or C is a max term. A bar or B bar or C is also a max term. This is not a max term. A or B bar is not a max term because it does not include the C, some form of C, either true or complement form of C. Okay, so now let's use these definitions to talk about how, in general, we can write an equation for any function using either sum of products form or product of sums form. Let's first talk about sum of products or SOP form. So this form is going to be a sum, an OR, of product terms, of AND terms. So an OR of AND terms. Okay, so any Boolean equation can be written in sum of products form. So let's see how we do this. So let's first consider our truth table that we've talked about before. So here's our truth table, and I've added a few things to the right. For now, we can ignore the output y. We're just going to look at these various rows of our truth table and the associated minterm. So a minterm is associated with each row. So each row has its own minterm. The 0, 0 row has minterm A bar, B bar. And that minterm is true for that row. And turns out only that row. So let's take a look at the 0, 0 row. A bar, well, A is 0, so A bar is 1. Here we have A bar and B bar. We get, well, 0 bar is 1 and B bar Well, B is 0. So 0 bar, the inversion of 0 is 1. We get 1 and 1, and yes, indeed, that is in fact 1 for that row. And we can consider the other columns or the other rows as well. So for example, let's take a look at the 1, 0 row. The minterm associated with that row is A and B bar. Let's look at A and B bar. So in the case of 1, 0, where A is 1 and B is 0, we get 1 and 0 bar, which is also 1. We get 1 and 1, and in fact, yep, that minterm is true for that row and only that row. Remember, a minterm is a product term that includes some form of each input variable. Okay, so it turns out that this term, this minterm associated with the row, is true for that row and only that row. So let's take A bar, B bar. We already said, yep, it's true for the one row. 0 bar and 0 bar is 1 and 1. We get 1. Well, let's see what it would be for these other rows. Well, if that term A bar, B bar, if we happen to have the input combination 1, 1, well, 1 bar, 0, and 1 bar, also 0, and we get 0. Or we could take the 1, 1, or 1, 0 combination. We get 1 bar, 0, and 0 bar, 1. Well, 0 and 1 is also 0. And you could do it for that last combination yourself. So a minterm is true for an associated row, its associated row, and false for every other row. So, and you'll notice that if there's a 0 here, we're going to have the complementary form of that variable. So if A is 0, we have A bar. B is 0, we have B bar in the minterm. So we can get that entire product to evaluate to 1. So now that we've defined these minterms that are true for a given row and only that row, now we can define some function. So let's say we have some function that's 0 in the 0, 0 case, 1 in the 0, 1 case, 0 in the 1, 0 case, and 1 in the 1, 1 case. And so now we can see that, well, you know what? We want this term to be included in our equation to force the output y to 1 in the condition that A is 0 and B is 1. We also want to have this term in the equation so that we can force the output to 1 in the 1, 1 case. So let's see what would happen if we just write y equals, well, we want it to be 1 in the case that A is 0, B is 1. So A bar B. So if we just had that as our equation, y equals A bar B, then the output y would be true when A is low and B is high, and only in that case. But there are other cases that we want the output y to be true, and in fact the other case is where, so we or it, say either that case or when A is 1 and B is 1. So we include that minterm in our equation as well, the A and B minterm. So the A bar B minterm will force the output y to 1 in the 0, 1 case. And the A and B term will force the output y to 1 in the 1, 1 case. So for sum of products or SOP form, we are forcing the output y to 1. We're forcing the 1s. So when I look at a function, I want to look at, hey, where is it 1? Well, it's 1 in both those cases. So I need to include those minterms, those product terms, in my equation and OR them together. So we can see that it's a sum. Here's the sum, the OR of products of AND terms. And here are our product terms. So it's a sum of products, SOP form. And here it is written down as well. So again, we look at our function. We look at the rows where the output is 1, where we want the output to be 1, and include those minterms in our equation and OR them together. So you'll notice this other column on the right where I've listed minterm name. So each row, in addition to a minterm, has a minterm name. So that minterm is called minterm 0. And you'll notice it's 0, well, that's the value of those inputs when interpreted as a binary number. So 0, 0, 0, 0, 1, that input combination for inputs A and B is minterm 1, minterm 2 is 1, 0, and minterm 3 is 1, 1. So we can interpret those inputs as a binary value, 1, 1, minterm 3. So that's one easy way to remember that. A common error here is to call this minterm 1, 2, 3, and 4. That would be wrong. Okay, so we can use these minterm names to also write our equation. We can write our equation then as a sum of minterms. In this case, well, there's a 1 there, so we want minterm 1, and sum that with minterm 3, which we also want to have a 1 on the output. And even more brief than that, I can write is equal to the sum of minterms 1 and 3. So sum of 1, 3. Remember that symbol, the sigma Greek character, stands for sum. And so we can write it, our sum of products equation, in either shorthand form with summation symbol, or we can write it in longhand form as A bar B or A and B, and that's our longhand form. If we want to manipulate these equations, as we will in the next module, well, we need to write it in longhand form. But they're both forms of the equation, shorthand and longhand form. So the other type of equation that we have for representing any Boolean equation is the product of sums form of the equation, or the POS form. Product, the and of sums of ORs. So an and of OR terms. Product of sums, POS. So in this form of the equation, we consider the max term for each row. Again, we ignore the exact function that we want to perform to start with. We just look at the max term associated with each row. For the 0, 0 row, for example, the max term is A or B. And that max term is false for its associated row, and turns out only false for that row. So it's true for any other input combination. So we can look at the A or B. For the 0, 0 combination of inputs, yep, 0 or 0 is in fact 0. Check, it's false for that row. And you can look at any other row and see, yep, it's false only for that input combination. So any other input combination, 0, 1, would be 0 or 1. That would be true. 1 or 0, that would be true. 1 or 1, that would also be true. So it's false for its associated row, and true for any other input combination. So our products of sums form, we're going to use these max terms and them together to create an equation. So we can take the same function that we had before, the 0, 1, 0, 1 function, and we want to now focus on the zeros, so where we want our output y to be 0. So we want it to be 0 when A and B are both 0. We also want the output y to be 0 when A is 1 and B is 0. So we can write our equation, our product of sums form of the equation, as y equals, well, that top max term, A or B. And if we just included that term, A or B, it would be false in the 0, 0 case and true everywhere else. which is close, right? That would give us y would have the function 0, 1, 1, 1. So it would miss that last 0. So we need to include another term to force it to 0 in the 1, 0 case. And in fact, we're going to include that max term there. So we're going to get A bar or B. So we look at the rows where the output y is 0, and we AND together the max terms associated with those rows. So in product of sums form, we are forcing the output y to 0. So we're forcing the zeros on the output. So this term, A or B, forces the output y to 0 in the 0, 0 case. 0 or 0, well, in the 0, 0 case, when A is 0 and B is 0, we'll get 0 or 0. That will evaluate to 0. We'll get 0 and, well, it turns out to be 1. But 0 and anything, that's going to be 0. We force that output y to 0 because of this A or B term. Similarly, in the 1, 0 case, well, when A is 1 and B is 0, in this case, we're going to get A bar, well, it's going to be 0. 1 bar is 0. Or B, which is 0. That term's going to evaluate to 0. We're going to get 0 and, well, turns out that's going to be evaluate to 1, but it doesn't really matter because 0 and anything is going to evaluate to 0. That 0 forces, because it's in an AND relationship, it forces that entire expression to evaluate to 0. So in products of sums form, we're forcing the zeros. So here, again, written or typed out for you. We're going to circle the rows where the output y is 0 and include those max terms in our equation and AND them together. So now we're going to get a product, an AND, a product, we'll use that same color, blue, product of sums or of OR terms. Product of sums or POS form. And again, remember that we're now forcing the zeros. In SOP form, we were forcing the ones, and now we're going to force the zeros. And you'll notice as well that we can also name these max terms 0, 1, 2, and 3. And again, those numbers, those subscript numbers, are just the binary value of the input combination max term 0, max term 1, max term 2, max term 3. So that name is just referring to the associated max term. So here's max term 0 means A or B, max term 1 means A or B bar, and so forth. And so now we can write it in shorthand, our product of sums form. Y equals a product, remember that's pi, that means the product of max terms 0 and 2. That's shorthand for saying, hey, max term 0 ANDed with, or the product of, max term 0 and max term 2. And again, remember this is our shorthand form of POS form. And then we have our longhand form as well. But they refer to the exact same expression. Just two different ways of writing the same expression. Again, if we want to manipulate the equations, which we'll do starting in the next module, we want to write it in the longhand form. Okay, so now we have two ways of writing our Boolean equations to specify a function. So the truth table specifies a function, and we can also write it in the form of a Boolean equation. So let's go to an example here. Let's suppose you're going to the cafeteria for lunch, and you're going to eat lunch. So this output E will be 1 if and only if it's open. So you have the sensor maybe on the door or sensing motion. Has to be open, and they're not just serving corn dogs. So maybe it's like a odor detector, smells the corn dog. It's like, that's the only thing they're serving. Not going to eat there today. So now we can write a truth table to determine whether or not you're going to eat lunch. So you're going to go into the cafeteria, you're going to eat lunch only if it's open. So these are the two cases where it's open. So remember, our truth table gives us all possible cases or combinations of our inputs, starting at 0, 0, the lowest value of the combination, so 0, all the way up to 1, 1. Okay, so our truth table gives us all possible input combinations. In this case, when open is 1 is in these two rows. So it's open, that takes care of this condition, or those two rows, and they're not just serving corn dogs. So corn dogs only has to be 0 in order for you to eat. So this is the only case where you're going to eat. In this case down here, it's open, but they're only serving corn dogs, so not going to eat. In the cases above, not even open. Somehow in this case, not open, and they're serving corn dogs, so maybe they're in the back having a corn dog party, but it's not open. So not going to eat in those cases. Okay, so we write this truth table for our function that we want. There's another way of saying the same thing. We can say, you're going to the cafeteria for lunch, you will not eat lunch if it's not open, or they only serve corn dogs. Basically, the true case, when will I eat lunch? And this is the opposite case, when will I not eat lunch? So let's show that you could have said it in either way. It's kind of glass half full, half empty. Really says the same thing. So you won't eat lunch, so E is going to be equal to 0 if it's not open. Okay, let's see. These are the two cases when it's not open. So not going to eat lunch then. Or they only serve corn dogs. So these are the two cases where they only serve corn dogs. So not going to eat lunch. In either of those cases, that one already was taken care of with not being open as well. So now we can know in every other case, we will in fact eat lunch. So when it's open and they're not just serving corn dogs, I'm going to eat lunch. Okay, so after we specify this truth table, we can now use either SOP or POS form, or in our case, we're going to write it in both forms to specify the equation for this functionality. So we look at our sum of products form, and we have, this is the specific function that we have. But remember, I want to emphasize here, these minterms are going to be those minterms no matter what the function is. This 0, O bar and C bar is the minterm associated with that top row, regardless of what the function is. And again, you notice that when in the input combination, when we have a 0 here, we have the complemented form of the variable. And when we have a true form in a combination, we have the true form of the variable for our minterm. If we have a true on the input combination, again, we have the true form of that variable. Okay, so that's how we can go from the truth table to the associated minterm. Okay, so here we have our function that we just figured out. And for sum of products form, I'm going to OR sum any minterm where the output is true. So E going to eat lunch if it's open and not just serving corn dogs. So we include that minterm in our equation. In this case, there are no other minterms to OR together. Okay, and we can also look at our product of sums form and write this same functionality. 0, 0, 1, 0 is the function we want to specify. And again, let's point out that our max term, remember, is false for that specific row. So for the 0, 0 combination, if we have a 0 in a variable term on the left, we're going to have the true form in our max term. So O or C OR together. Here's another example, 0, 1. Well, this is the 0 in the input value, so O is a 0, so we'll have the true form. C is a 1 here, and so we're going to have the complement form in order to get that entire term to evaluate to false. We're going to get 0 or 1 bar, which is 0. 0 or 0 is going to evaluate to 0. Okay, so now that we've reviewed our max terms, now in product of sums form, remember that we circle the zeros. So we're going to circle each of these rows here. So we're forcing the zeros on the output. We're going to include those associated max terms in our equation and AND them together. So we're going to get E is equal to O or C, max term 0, and O or C bar, max term 1, and O bar or C bar. So this term is going to force the output E to 0 in the 0, 0 case. O equals 0, C equals 0. This term here is going to force the output Y to 0 in the O equals 0, C equals 1 case, because it'll evaluate to 0 in that case. And the last term is going to force our output E to 0 in the O equals 1, C equals 1 case. We're going to get O bar 0 or O bar 0. That entire term is going to evaluate to 0. We're going to get 0 and anything is going to force our output E to 0. And we can also write these, as we've talked about, in the shorthand form. This is the sum of minterm 2, 0, 1, 2, minterm 2. And this, the product of sums form of the equation, we can write as the product of, or the AND of, max terms 0, 1, and 3. Okay, so you may ask yourself, what's going on here? We said this is the same function, and we've written it in 2 different ways. So we've written this equation in 2 different ways, and gosh, those equations look pretty different. How do we prove that they're in fact specifying the same function? Well, one way is to do what we've done already, show for each input combination, so each possibility on the inputs, the output evaluates to the same thing. So, for example, in the 0, 0 combination, this term evaluates to 0 and 0 bar, which is 0 and 1. So in fact, we do get 0, right? We're going to get 0 and 0 bar, which is 1. Yep, that evaluates to 0. We also can get the next case, which is our 0, 1 possibility. Well, now we're going to get 0 and 1 bar, which is 0. Yep, that definitely evaluates to 0. Check. We got that one to work. And now we can look at the next combination, 1, 0. We're going to get 1 and 0 bar, which is 1. There we have our minterm forcing our output to 1, as we wanted. And finally, we can check the last possibility, 1 and the 1, 1 combination. We get 1 and 1 bar, which is 0, and we get 0 as expected. And we can do the same thing for our product of sums form of the equation. We can look at our terms here and say, okay, well, in the 0, 0 case, what do we get? We get 0 or 0. This first max term, 0 or 0, is going to be 0. We're going to get 0 or 0 bar, which is 1. 1, and we can get 1 or 1, 0 bar, O bar or C bar, 1 or 1, we get 1. All of these ANDed together. Well, that 0 right there, as expected, that max term forced E to evaluate to 0, as expected. And we can do that for every possible combination, and we'll see, okay, for the 0, 1 case, we're going to get 0 or 1, evaluates to 1. We're going to get 0 or 1 bar, we're going to get 0 or 0, evaluates to 0. We're going to get 1, 0 bar, or C bar, it's going to be 0, that's going to evaluate to 1, 1, and 0, and 1. Well, that 0, as expected, forces our output E to be 0, because 0 and anything, 0 and an AND relationship, force, no matter what the other values are, even those are both 1, 0 and, well, all of these terms have to be 1 in order to get the output to be 1. And then we can look at the other two combinations where we have 1, 0, 1 or 0 is going to evaluate to 1. We're going to get 1 or 0 bar. It's going to be 1. And here we're going to get 1 bar, which is 0, or 0 bar, which is 1. We're going to get 1. In this case, there's no term. This max term isn't included in the equation, and so there's no term to force it to 0, and that output evaluates to 1, as expected. And finally, the last input combination, 1, 1, where 0, O is 1 and C is 1. We're going to get 1 or 1. Yep, that evaluates to 1. This one is 1 or 1 bar, which is 0, 1. And we're going to get 1 bar, which is 0, or C bar. C is 1 in that case, so 1 bar, again 0. And we're going to get 0. All those ANDed together. That term, as expected, that O bar or C bar forces our output to 0, and we get the 0 that we expected. Again, remember our products of sums form, POS form, is forcing the zeros, forcing the output to 0. Okay, so that's one way that we can show that they're equal, because, well, they result in, both of those equations result in the same function for every possible input combination. We don't know what the input is, but we can evaluate it for every possibility. So for every possible input combination, the output looks exactly the same. So for the 0, 0 case, they both evaluate to 0. For the 0, 1 case, both of the outputs would be 0. For the 1, 0 case, they both evaluate, those expressions both evaluate to 1. And for the 1, 1 case, they both evaluate to 0. Another way that we can show that these equations, the sum of products form of the equation and the product of sums form of the equation, that they're equivalent, is we can use what's called Boolean algebra. So just like in regular algebra, we manipulate variables and minimize them, for example, we can do the same thing with Boolean algebra. And it turns out some of the rules for Boolean algebra are actually exactly the same as for regular algebra. And there are some different ones as well, which we'll talk about in some of the next modules. So let's go through some other examples of going from words to a Boolean equation. So here's another example. We'll go to the park. So P is going to be equal to 1, this P output, if and only if it's not raining. So R is 0. And we have sandwiches. So S is 1. Not raining. And we have sandwiches. So we'll go to the park if it's not raining and you have sandwiches. So we can go directly from a statement, from words, to an equation. You could also put this into a truth table. R and S as our inputs, and going to the park as the output. We write out all the possible input combinations in our truth table, starting at 0, 0, and going to the highest binary value, in this case for 2 inputs, 1, 1. So we're going to go to the park if it's not raining. So that's the not raining cases, those two. And we have sandwiches, so only that case. And you can see that we've written this in sum of products form, just by going directly from this expression to our equation. The second way of doing it is redundancy. This is another way of doing it, but redundancy. So in addition to going directly from the statement to the equation, as we did here, you could also go from the statement and fill out a truth table. The easiest way is the first method that I showed, going directly from the statement to the equation. Here's another expression. You'll be considered a winner, W is the output, if, and only if, we send you $1 million, or we send you a small notepad. So you'll be a winner if we send you $1 million, or we send you a small notepad. And this is used by marketers quite a bit. You have just won $1 million, or a small notepad in very small letters. So here's another example. You can eat delicious food if you make it yourself, or you have a personal chef and she or he is talented but not too expensive. Okay, so you're going to eat delicious food, E is the output, if and only if you make it yourself, or put that here, or you have a personal chef. Cool. That would be cool. And she or he is talented but not too expensive. So in Boolean algebra you can replace any but not with an and not too expensive. Here's another example. You can enter the building if and only if you have a hat and shoes, a hat and shoes, hat and shoes. Again, that and symbol is optional. Hat and shoes, or just a hat. Okay, so you show up to the building, you have a hat on, do they let you in? Yep, they do. You show up to the building, you have a hat on and shoes on, do they let you in the building? Yep. You show up to the building, you have a hat, no shoes on, do they let you into the building? Yeah, they do because of this term. So this is the correct expression for the statement above, but you may realize that, hey, we could have reduced this to really, logically, this is the same as saying you can enter the building if you have a hat on. This term is already covered by that term. So this going from this first expression to the second expression is called minimization, or reduction, reducing the equation. But if you're asked to go from this Boolean expression to an equation, that's the right equation to go to. If you're then asked to minimize the equation, that next step would be to minimize it. And logically we can see, yeah, that's true. That expression, E equals H, you can enter the building if you have a hat on, is logically equivalent to you can enter the building if you have a hat and shoes on, or a hat. Because this term, you can enter the building if you have a hat on, or hat and shoes already covered that second case. Here's another example. You can enter the building if you have a hat and shoes on, or a hat and no shoes on. Okay, so this is the correct expression, Boolean expression or Boolean equation for this statement. So that is the answer if you're asked to turn some statement into a Boolean equation. That's the correct answer. And now we can think about it logically and think, okay, well, let's see. I can enter the building if I have a hat and shoes or a hat and no shoes. So I show up with a hat and no shoes, they let me in. I show up with a hat and shoes on, they let me in. Gosh, I guess it didn't even matter if I had the shoes on. So minimization, again, we can minimize that expression to be just E equals H. But this expression, this equation up here, is the representation for that statement. And then we may realize, hey, you know what, I can simplify or reduce that and realize that expression is equivalent to just, hey, if you have a hat on, you can enter this building, no problem. Okay, so that second step, that minimization step, is what we're going to talk about in the next modules.